Today we'll be talking about scientific notation, unit conversions, and scaling factors. You should have a lot of scientific notation in high school and all your preceding math courses, science courses, and everything, but I'm just going to review it quickly because we kind of have to start with that. I just want to review how we handle the zeros and the decimal places with that. And just a little quick review here. It's not going to be very extensive. So I'm going to start off with a really tiny number, which is the wavelength of green light, which is about 520 nanometers. A nanometer, if you recall your SI prefixes, a nanometer is actually 10 to the negative 9 meters. So 1 nanometer equals 10 to the negative 9 meters. Now, you've probably had this extensively, and let's make that look more like a 9 rather than a blob. You've probably had extensive coverage of scientific notation, as I had mentioned earlier. What does that negative 9 mean? Well, that kind of means decimal point to decimal point. If you can imagine, there's essentially a decimal point here. It's different if there's actually a 0 over here, but this is where that number ends, essentially, before it breaks down into decimals. So from decimal point to decimal point, I have to have 9 numbers. So what do I mean by decimal point to decimal point? I have a decimal point here, and I got to have 9 numbers going that way. That's what that negative 9 tells me. Okay, so let's just do that quickly here. I'm going to use a different color. Let's use green because we're using green light. So I need 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. Okay, but I've already got the 520, so that's going to cover the 3 on this end. Okay, so let's write that 520 here. And then the rest are all going to be zeros. So you can see the advantage of why we use scientific notation here. Okay, because this number it's going to be really ugly on paper, especially if you're carrying out a number of calculations. So it's a lot easier just to convert it to 520 nanometers, which I should have written, and I'm going to write this out now, is really 520 times 10 to the negative 9th meters. Okay, so that's a lot easier to handle than this is to handle. And I forgot my units, bad me. This is why we use scientific notation. Again, let me just carry us on a little bit. Let's put a note here. Note that this number up here, this 520 times 10 to the negative 9th, this could also be written as 5.20 times 10 to the negative 7th. So in that case, this is what I was talking about with decimal point to decimal point. In that case, we've got the decimal point here, this decimal point after 5, and I've got 7. So I need 7 spots from here to here, but then these two numbers here matter and they carry on afterwards. So the negative 7 means I carry that 5, which is before the decimal point, to here, and then whatever's after the decimal point I got to carry out for the rest of that. So 520 times 10 to the negative 7th meters is also equal to 520 times 10 to the negative 9th meters, or 5.20 I should say. So that's how you kind of handle the really small numbers. And so just for review, let's talk about maybe a large number. So in this class, we're going to be using the astronomical unit, which is the distance from the sun to the planet Earth. It's easier to break down into astronomical units because they give us a much smaller numbers to deal with rather than kilometers or miles like that. And you can kind of see when I write this out that 1 astronomical unit, as we abbreviate it, AU, is equal to 93 megameters. Well, I shouldn't say equal, it's approximately. It's just a shade under that. But for this purpose, we can just say, you can round it to 93 megameters. So what's a megameter? Again, with the scientific prefixes, that just means million, or 10 to the 6th. So let's just define that quick. 1 megameter equals 10 to the 6th meters, and I'll put in parentheses here, also known as 1 million meters. Okay, so the 93, again, we've kind of tricked you a little bit with the 5.20. So that 93 megameters actually means 93 times 10 to the 6 meters, or I could write it as 9.3 times 10 to the 7th meters. Okay, so what I did here was I just added another 10 to this multiplication. So basically, this is really moving the decimal point over 1 spot by adding another 10. So I moved it a little bit to the right. So let's say decimal point to decimal point. Let's use this one first here. Okay, so basically, I'm going to have the amount of zeros before the decimal point. This is kind of a little bit different than that conceptually. So I'm going to have 6 zeros before the decimal point. Okay, 2, 3, 4, 5, 6. So the decimal point is going to be here. But I also have 93 in front of that. All right. So that's 93. That's 93 megameters, or 93 million meters. So that's again, as I was talking about with how this, when you're carrying out calculations, writing out that whole number is rather ugly. It's easier just to write the numbers like this and then just deal with the exponents separately. We'll get a little bit more into that with unit conversions. So let me just try this again, but let's look at it this way. So now I'm going to have 7 digits after the decimal point. So I'm going to have 9, and I'm going to have 7 until I get to here. So that's going to be 3, which is 1, 2, 3, 4, 5, 6, 7. And we get our same result, 93 million meters. So this is really should just be review for you. You'll get some practice like that. You'll just get a little bit familiar with that again. I recommend using scientific notation whenever you can. Because carrying out long digits like this can lead to a lot of mistakes. You forget to write a 0 in the middle there, or you forget to write an end there, a 0 on the end, and then your answer ends up being off by a factor of 10, a factor of 100. So a lot of times, if you're dealing with big numbers like this, it's a lot easier to use scientific notation. Here I have a meter stick. Why do I have a meter stick? Well, I'm going to be talking about unit conversions, and there's a lot of little information on this 1 meter stick. We're going to be learning a method called multiplying by ones, and I'll explain that in a little bit. It's a pretty simple method once you get over maybe some discomfort of not being familiar with it. So in this meter stick, this is 1 meter from hand to hand. I've got 1 meter here. There's all these other little numbers, right? There's a 50 there, a 60, 70. Those are centimeters. So there's 100 centimeters in this 1 meter. So if I went down to here, this would end at 100 centimeters. Also, I've got all these little ticks on here, these little tick marks, which are really hard to resolve here. These are really tiny increments. These are known as millimeters, and there's actually 1,000 of those in here. So this all equals the same thing. 100 centimeters equals 1 meter equals 1,000 millimeters. I think I said that right. So there's something else interesting about here. So this is in the SI unit system that we use in science. Here in the United States, we use the English system. Well, this one has the English system on back. Now this is the amount of inches. And as you can see, it doesn't quite equal an actual number. It doesn't really end at 39. It just goes a little beyond 39. It's kind of hard to see with that metal casing on there. But there are actually 39.37 inches in 1 meter. So 39.37 inches also equals 1 meter, which is actually this same distance. That distance doesn't change. Even though the numbers change, this is the same distance from here to here. It's 39.37 inches. It's 1 meter. It's 100 centimeters. It's 1,000 millimeters. Now that we've kind of explained how something like this could be all different numbers but all equal the same thing, distance, 1 meter, they all equal the same amount of distance. They're just defined different depending on what units you use. So I'm going to walk you through an example of a method called multiply by 1. And I'll explain a little bit about why we say that it's equal to 1. So let's just start off with an example of Mount Rainier. Mount Rainier is, if I spell this right, 1E, right, I think? Yeah. It's 4,392 meters tall. Now, on a clear day in Seattle, we can see Mount Rainier every now and then. Every now and then on my drive home, I actually get to see it, and it's quite spectacular. It's a pretty tall mountain. It kind of sticks out relative to a lot of other things. It's almost the same height as downtown on my drive home. So let's use that as an example, and let's convert this into feet. Let's say, how many feet is Mount Rainier? let's first look at the fact that this is 4,392 meters. Like, I know a kilometer is like 1,000 meters, so I know this is 4.392 kilometers. Maybe you don't look at that and see that automatically, but you know this is 4.3 kilometers, so you're going to be talking about something on the order of miles. Now let's just say I'm given something on a test, or let's just say I want to know this off the top of my head, and I know that there are 5,280 feet in a mile. So this is going to be on the order of miles. So I want to get to, I want to somehow convert and get it over to miles. Let's just say I know that conversion factor. So I'm going to say in 1 mile, there are 5,280 feet. Now, why did I write it this way? This is what I was talking about with with this equal to 1, because this is the same distance as this is the same distance. So if I would convert these to the same units, I would have, either this is equal to 1 mile, so I'd have 1 mile over 1 mile, or I'd convert this to feet, and I'd have 5,280 feet over 5,280 feet, which is equal to 1, right? So you're not changing any of the things. All you're doing is converting from feet to mile when you use this conversion factor. And I'll be using that term conversion factor a lot this week. So let's just say I know this, right? I'll put that in parentheses. Let's just say I know this. Okay, that's one of the conversion factors I know. What else do I know? Well, this one only because I teach astronomy do I know this off the top of my head. But I know that in 1 kilometer there are 0.6213 miles. Okay, so in 1 kilometer there are 0.6213 miles. So this is less than 1. So basically a mile is, I don't know, like 62% of a kilometer. So a kilometer is much smaller than a mile. I shouldn't say much smaller, but it's smaller than a mile, because if I get up to one mile down here, this would go up to like 1.14 kilometers, something like that. I don't know that one off the top of my head. 1.4 kilometers, something like that. But again, this is the same distance as this. That many miles, or like 0.62, like a fraction of a mile, is equal to 1 kilometer. So if I would convert this to the same units, divide over the other, this would equal 1. So this is, this ratio is equal to 1. So we read our conversion factors as ratios. And this method works really well for converting units. There's one other thing that I'm kind of missing here, but I've got this in meters. And everyone should kind of get familiar with these. Most people are at this point familiar with these prefixes. I talked about them earlier. But a kilometer is 10 to the 3rd meters. So I know that in 1 meter, or 1 kilometer, I should say, there are 10 to the 3rd meters. Now I have all the conversion factors I need to figure out what Mount Rainier is in feet. So you might be saying, well, there's a bunch of numbers on there. I'm a little bit intimidated. How do I even go about this problem? Let's start off with the thing we want to convert, 4,392 meters. So I'll write that over here, 4,392 meters. Let's start off with that. Now we're going to be talking about multiplying by ones. By multiplying by any of these numbers, I actually don't change this distance. All I do is change the units. That's the key when you say multiply by 1. All right, so the first thing I want to do is cancel the units here. Let's just separate this out so that it looks more like a unit, okay? And instead of the multiplication symbol, I tend to like to use parentheses. So first thing I want to do is get rid of meters. So I've got a ratio here, okay? This is kind of like an algebra where you have an x over an x and the x's cancel. You want to have meters down here so that these cancel. Okay, so what do I have over here? Well, I want to get to kilometers because I know how to get to miles from there and I know how to get to feet from there, okay? So first thing I want to do is get rid of the meters, and I've got this conversion factor, and so I've got 1 kilometer is equal to 10 to the 3rd meters. So now, this is kind of the key. If I went like this, then my only unit left, because this isn't canceled, these two have canceled, my only unit left is kilometers. So if I multiply this out, which is actually when it's written like this is actually 4.392 divided by 10 to the third, but it's also multiplying it times 1 over 10 to the third. I know a lot of students get confused with that. But if you divide this by 10 to the third, you'll get 4.392 kilometers. So that's what we have right now, okay? So you can do this step by step, have a whole bunch of calculations, but it's really ugly. So I'm going to try to show you a much easier, simpler way, and I walk you through it in the labs, and there's lots of examples in the lab introduction. So next thing I want to do is I want to get to miles. So I got 1 kilometer, I got that ratio right here. I got this guy right here. Okay, so I want kilometers down here. Now this is another thing people get confused about. If I flip this and I have 0.6213 miles per 1 kilometer, if I flip that ratio, it's still 1. I have not changed the value of this ratio. So I can flip them accordingly as far as how I want to use them and what units I want to cancel. So I've got kilometers down here, so I got 1 kilometer down here, and I've also got 0.6213 miles up here. These will cancel. So now, if I take 4,392 times 0.6213, then divide that by 10.3, or you can go in order like this, then my answer is going to be miles. The kilometers have canceled out, the meters have canceled out. Okay, so now I would have that answer in miles, but I want to get to feet. So I've got one more step to do. So I want to multiply it times one more factor here. Now now I have miles up here, so I want to write miles down here because I want those to cancel. So again, as before, I have to flip this to make sure that I get it right. So in 1 mile, I have 5,280 feet. The miles cancel, and again, just as before, you just multiply all these numbers out. You multiply 4,392 times 1 over 10 to the third times 0.6213 times 5,280 feet. Now, at this point, I already know I have the right answer. That's the thing. Someone says, well, how tall is that in feet? And they can do a bunch of, they don't know what they did necessarily, but writing them all out in one line like this makes it a lot easier. Let me try to break this down just a little bit more here. Let's grab a different color here. These are all the unit conversions. I haven't done anything. These are all 1. If I multiply these all together, I haven't changed anything about this factor over here. Okay? This over here is the thing we're trying to multiply. This is the thing we're converting. So I don't know what to call it, but the thing we're trying to... So basically, we had this distance, and we used this to convert the units without actually changing the original actual height of that object. All we're doing is changing it into the English unit system from the metric unit system. So when I multiply that all out, I get approximately, so let's change it to approximately, 14,408 feet. So that's how tall Mount Rainier is. Now there's lots of examples we can do this. I suggest actually writing them all out in one line like this so you can keep track of your units. It's a lot simpler. That way you know that when you have the right units, meters cancel with meters, kilometers cancel with kilometers, miles cancel with miles. The only thing that didn't cancel was feet. I know this answer is going to be in feet. I know it's correct. That is the power of using this method. Rather than doing it step by step. You could do it step by step, but then you lose kind of track of the units. You haven't seen clearly that you know you have the right answer because you're going from number to number to number to number. And if you mess up one of those steps, then you end up with the wrong answer. So I recommend really practicing that way. In the labs, you will be able to walk through it step by step, and I have lots of examples in the lab introduction. So these were the little knickknacks that you had just saw, casting a shadow. This was the camel person. As you can see, this is not to scale because the camel and the guy are much, much taller than the pyramids, and that's just not realistic. I mean, in reality, the camel would be, let's see if I can get my hands over there. The camel would be like, that high or something. So this is a scale model, if you'll say. Oh, well, we'll check that pretty soon, of the Great Pyramids in Egypt. So the reason why we scale in astronomy is because astronomical units are so large, light years are so large, that when you look at them in meters and kilometers, it's hard to get a sense of how they actually truly relate to one another with distances. Many people have made scale models of the solar system in science classes in high school or in introductory science classes in geology and classes like that at the college level, and we're going to calculate that in our lab, but we're not going to actually like mark it out in a parking lot or anything like that. But I want to give you a sense of what it means to scale everything. So if this was the actual, like if I wanted to scale everything to the size of this pyramid, and I wanted a scale model that was accurate, and this was the second highest pyramid, I would want somehow to convert that factor the same each time, so that whatever I used to scale it down to this height, I would scale that same amount this height, and then so they'd be an accurate representation. We'll find out if these are or not. Same with this one. The same factor is going to multiply this. So everything scales proportionally by the same factor. So let me talk about a scaling factor first. You should be able to see a picture right about now of the measurement of the height of the pyramid. It turns out that it was, in measurement, 6.8 centimeters, about 6.8 centimeters. So this is what I measured, and I'm going to put this in a different color just so you don't get that confused with the multiplying by ones thing, because this is going to be, the scale model is going to be over here. Okay, so the scale, I'll put in red, was 6.8 centimeters. So now if we want to scale all the pyramids proportionally, I've written them out here. I'm not going to try to pronounce these because I'm not an Egyptologist, so there's no way I can pronounce this. I just call it tallest, middle, and we'll call it this one, the smallest. So these are the original heights of the pyramids. So there's been some erosion over time, so they're not quite as tall as this now, but originally built, they're supposedly about this height originally when they were built. So now let's scale these other two the way this one was scaled. So we're going to scale it using the same factor that we did there. For a true scale model, they should all be equal when I actually measure them out. So what I need first is a scaling factor. Okay, so a scaling factor. A scaling factor is what you multiply all the distances and heights and things like that in a system so that you're making a scale model that's accurate. So this is going to be a little bit conceptually weird, but architects do it, city planners do it, and it isn't just astronomers who do it. So it's like a very common thing. I mean, people who make knickknacks, they use scaling factors, although, again, we'll find out if that's accurate or not. So what I want to do is I'm making this smaller. So this is actually 146.5 meters tall. This is much smaller, okay? So I want to multiply something that'll shrink it down. So I know that this is going to be in the top. So I'm going to have my 6.8 centimeters, and I know that this is going to be in the bottom, 146.5 meters. Now if I converted that to meters, this would actually be the percentage of height of this relative to the Great Pyramid, and it would be a really small number. But we don't want to convert the units yet. This isn't like the multiplying by one thing, because this doesn't equal, it equals 1 in our scale universe, but this doesn't equal 1 at all. We don't want to cancel those units out. We want to use this as a conversion factor, so we can multiply everything in that model universe, model city, model pyramids, model everything by that same number, so that everything proportionately shrinks. If you're scaling up, everything gets bigger. So if you're going from an atom and bigger, you'd scale up to be bigger. And then you flip these types of things. So what I want to do here is first this smaller number. So I'm going to calculate it out. And I get 0.0464 centimeters per meter. That looks weird, right? That definitely looks weird, centimeters per meter. But as you'll see, it's really convenient if we want to scale other things like that. So now all I have to do is multiply this times this number, and that'll give me what the scale height will be if this is an accurate scale model for the second one. Okay? So let's just do that quick. Right now I think I'll just do it over here. Okay, so I'm going to take this number here. This is my scaling factor. I developed that by taking this scale pyramid over the gigantic real pyramid. I use that ratio, and that's the ratio I'm using to scale here. Okay, so if I take 0.0464 centimeters per meter, now I multiply it times that, which is 143.5 meters. So now I'm multiplying my scaling factor times the actual original height of that middle pyramid. Now, as in before with the unit conversion, I've got meters over meters here, because this is really, over 1. So I've actually got meters divided by meters. The meters cancel. My answer should be in centimeters, and that should theoretically be the height of this guy. So when I actually multiply that out, I get that approximately equal to 6.67 centimeters. So let's kind of keep track of that up here. So it should be 6.67 centimeters here. So that's what it should be. Okay, now let's just take the next pyramid here. So once you've got this conversion factor, this goes really, really quickly. So let's take that. Let's start with our original scaling factor again. Let's multiply it times 65.5. And if there's any Egyptologists watching me, just shaking their head at me, that's fine. So I cancel out the meters. I'm just using it as an example because of the knickknacks I found. So the centimeters is what's going to be left here, and my answer then is going to be in centimeters. So I'm scaling this down to what this should be in this scale model. Okay, so it turns out that if you multiply this out, you get 3.04 centimeters. So that's how tall it should be. So let's write in that up here, 3.04 centimeters. Okay, so it's that simple. You just develop a scaling factor, this thing over here. You develop that, and you can multiply everything. I could multiply my height to find out how high I was, or how tall I was in that system. I could multiply this camel to find out how tall this camel really should be in that scale model, which would be really tiny relative to the scale. So it's really that simple. Once you have the scaling factor, just conceptually, you have to know whether you're going bigger to smaller or smaller to bigger. But once you have that scaling factor, then everything in your system or whatever gets multiplied by that, and you end up with what should be a proper scaled system. Okay? If it's scaled correctly, like a city, like a building, or an architectural plan, something like that, if it's scaled properly, then it should be all multiplied by the same scaling factor. So now, let's see if this actually compares. Okay, I actually did take a ruler and I measured the heights of these guys for the peaks. And as I wrote this one in red before, I'm going to write down what the actual heights were when I actually measured them physically. So this ended up being 5.6 centimeters about, and this one ended up being 4.5 centimeters. So apparently, the people who developed these knickknacks, they just did it conceptually. They did not actually scale them correctly. So, but nonetheless, the whole point is the same. This is what it should be, even though the measured values were quite off. This is what it should be if you're actually scaling those pyramids the same. Now you can scale anything using this method. So it's really not as confusing as you think it is, because if the scaling factor, all it does is make everything bigger proportionally or make everything smaller proportionally. All that is, the conceptual part of having something weird like a centimeter over a meter and not canceling those units, that might be a little uncomfortable, but just consider what you're using the factor for. You're not using it to convert units, although some steps in there you might have to, but you're not using it to convert units, you're using it to scale things down. And with that, this guy would be much, much smaller.